far, we've looked at plane stress elements. So there's stress element in the XY direction. There's three stresses which go with it: sigma x, sigma y, and tau xy. We drew Mohr circle, which basically tells us what the stress is at an inclination. Given a random theta, we can find the stress. We can also find the principal stress. Now, it turns out that most times we are dealing with three-dimensional objects, which means the stresses have not just sigma x, sigma y, tau xy, but they have more components. And so this is alluding to that. So 3.7 is generalized general three-dimensional stress. Stress. So we drew a sort of a rectangle or a square and showed the stresses. If you wanted to go in 3D, then we want to draw a cuboid. Okay. And then let's show the axis. X, Y, and then Z by the right-hand rule should be pointing out of the plane. Okay, so similar to 2D stress, we draw the stress at each of the planes. And so since there are 6 faces to the cube, there will be, what I'm going to draw is for one face, but you can draw that for all 6 faces. So I'll draw it for 3 faces because those are unique, and then you can draw it for the other 3 by just taking the same thing and rotating it by 180 degrees. So on face, so this face is the face which is along the YZ plane. And so that will have a normal stress, a shear stress, which will be in the Y direction, the top, the one which is pointing up, and then one which is pointing in Z direction. So the stress is, this is sigma x because it points in the X direction and it is normal to the face. This stress, which is pointing upwards, the convention is the first index. The first index gives us the normal to the surface. So the normal to that face is the x-axis. So that's the first index. And then the direction is y. So similarly, for this stress, we have tau. The normal is x, and the direction is z. And then you can just do that for each of the 6 faces. So sigma z, this one would be tau. The normal to the surface is z, and its direction is y. And then this one is going to be normal is z, direction is x. Okay, and the last face, the third face is, this is sigma y. For this stress, we have tau. Normal is, this is normal to the face y, and the direction is x. And then tau y z. Okay, so it's kind of cluttered with 3 forces, but 3 stresses, but you have to draw that for each of the 3 which are not shown. It just becomes so cluttered. But you will essentially draw the same things, but point the arrows in the right direction, which will be exactly equal and opposite to the stress which I've shown. So for example, if there's sigma x here, there will be a sigma x in the other direction on that face, which is opposite to the face I've shown. Okay, so this is getting fairly confusing, right? I mean, sorry, fairly hard, right? How do you analyze something which has three-dimensional or so many stresses? So let me just list down the stresses we wrote down. So first we have sigma x, tau xy, tau xz, sigma c, tau zx, tau zy, then sigma x, tau, sigma y, tau y, z, y. So we see that there are 9 stresses in 3D. And for 2D, we wrote this down earlier, sigma x, sigma y, tau xy is 3 stresses for 2D. Right, so we used those stresses, sigma x, sigma y, tau xy, to do analysis using the Mohr circle. So what you do in case of 3D is you do something very similar. Then you take these stresses in pairs or in triplets, sigma y, sigma z, tau yz, sigma z, and by the way, I should have written this, tau xy is so this should be equal to tau y, right? That's complementary stress. Tau zy, and then sigma z, sigma x, tau cx equals tau xz. So 3 stresses for 2D, the same thing. So what we are looking here as plane stress with sigma x, sigma y, tau xy, that's one phase. Then we do it for the second phase, sigma y, sigma z, tau zy. And then what we can do is we can draw 3 more circles, one for this, one for this one. You know what, let me just not call that 1, 2, 3, because I know it will be confusing. We had 1, 2, and 3. So we draw Mohr circle for case 1, Mohr circle for case 2, and Mohr circle for case 3, right? You can do that because you have 3 numbers representing plane stress. So we'll draw 3 Mohr's circles for 1, 2, 3. Okay. So this will give us essentially sigma A, sigma B, sigma C. So even though you do see that there are there'll be 6 principal stresses, right? The first equation, the first line gives two principal stresses, the second line gives 2 principal stresses, third line gives 2 principal stresses, 6. But what you'll see is that you actually end up with only 3 principal stresses. Those values from one of the principal stress from 1 will match the principal stress for 2 and so on. So what we'll do is once we have these principal stresses, we can order them in this order. Sigma 1 is greater than sigma 2 is greater than sigma 3. Okay, so we basically rearrange the stresses such that the maximum one is, we'll call that sigma 1, the minimum is sigma 3, and the one in between is sigma 2. So rearrange in this order. And once you do that, we'll end up with 3 more circles. Okay, let's say this is the smallest one. The smallest one will correspond to the pair sigma 2 and sigma 3. Then there will be a slightly bigger one. Okay, so that will correspond to sigma 1, sigma 3, the maximum and the minimum. And then finally, you will also get one corresponding to sigma 1 and sigma. So this one will be sigma 1 and sigma 2, my bad. Sigma 1, sigma 2 will give this, and sigma 1, sigma 3 will be the biggest one. And I'll summarize all this in a bit. Everything is right. They should actually line up. This looks okay. Okay, so again, this is sigma axis. This is the tau axis. Okay, so now this point would be the maximum stress. This would be the second one, sigma 2 and sigma. Yeah, I just messed the figure up. This should be, by the way, this should be sigma 2 and sigma 3. Just by looking at the figure, you can see that the smallest one circle should be corresponding to the extremes, right? So then you can draw the maximum stress. I'll call it tau 1, 3, tau 2, 3. And this will call tau 1, 2. There's something wrong. So I think I'm messing this up. Let's see. Let's just take an example, 10, 5, and 1. So if that's true, then the bigger circle, so 10 minus 1 divided by 2, that should be the rate of the bigger circle. So yeah, so that can't be true. It has to be that this is sigma 3. It has to be giving you the biggest circle based on, just because the radius is sigma. So the R max should be sigma 1 minus sigma 3 divided by 2, right? So that would be the biggest one. So it should be 10 and 1. Sigma 3 has to be there. Otherwise, that calculation won't make sense. This should be sigma 2. And then this should also be renumbered. Sigma 1, 3, tau 1, 3, tau 1, 2, tau 2, 3. Okay, so the taus are actually sigma. So you can see that it's basically the radius of the circle, right? That's the radius of the biggest circle. But the radius of the biggest circle is nothing but sigma 1 minus sigma 3 divided by 2, because sigma 1 minus sigma 3 is the diameter of the biggest circle. So tau 1, 3 should be equal to, if you like, the radius center, which is sigma 1 minus sigma 3 divided by 2. And then similarly, you can apply the same logic to find tau 2, 3, which will be sigma 2 minus sigma 3 divided by 2. And then tau 1, 2, which is sigma 1 minus sigma 2 divided by 2. Okay, so the reason why we're interested in analyzing a general 3D stress element and drawing 3 Mohrs circles is that when we are designing something for maximum stress, we are interested in the maximum of that, the biggest circle, right? The biggest circle will give the biggest stress. And the biggest stress would mean that that stress is most critical for that particular stress element, which means that when the element fails, it's because of the principal stresses which have the maximum value. So sigma 1 and sigma 3 are going to be critical. Sigma 2 is not going to be critical because it's intermediate. So a typical procedure would be, if you have a general 3D stress element, you first draw the 3 Mohrs circle. You first either draw the 3 Mohrs circle or find the 3 principal stresses and use the extremes, sigma 1 and sigma 3, to find the stress which is most important. And then you proceed with design using the maximum stress. And this is something which will come up again when we talk about designing shafts for different loads. Okay. So we'll